Hello everyone, welcome to this video. This time we're going to be proving the orthogonality and discussing the completeness of the infinite square well wave functions. So in the last video we showed that this psi of x, the wave function, remember that the actual wave function is also going to have a time dependent part, right? But we said we're still going to call this psi of x the wave function, although it's actually just a stationary state. But just for ease of communication, we're going to be calling it the wave function anyways. Well, we saw that the form of these wave functions is going to be square root of 2 over a times sine of n pi over a times x. A here is the length of this square well, and since there's an n dependence, we're going to have to putting an n down here, right? Because there are going to be several allowed states, and each one of those is going to have an energy level, En, which is just going to be n squared pi squared h bar squared divided by 2ma squared. So when we put this into this wave function that also considers the time factor, we get the following results. Now all of this is something that we already showed. If you don't know why this is, you can just go back to the previous video, and this is going to be times e to the minus I e t over h bar. Now, but since energy, En, since energy is this over here, we can just write this as minus I times n squared pi squared h bar. This squared got cancelled with the h bar that was in the denominator, times t. So this is going to be these wave functions. So that's what we showed last video. Now we're going to prove that different wave functions for the different states, for example psi1 and psi2, these are going to be orthogonal. So what that means is that if you make the inner product between them, basically if they multiply, it's not really that simple, but for now, if you have never seen this concept before, it is basically that if these two quantities multiply, then the result is going to be 0 if these numbers are different. So in general, we say that this integral of psi m and psi n is going to be 0. That means that they are orthogonal. So let us prove that. So the way to do that is just to replace this expression in here for m and for n. So this is going to be the integral from 0 to a, and psi m is just going to be square root of 2 over a of sine of m pi over a times x. And now we write the psi n, that's just psi m, and whoops, I meant to write what it means. So this is just square root of 2 over a sine of n pi over a times x dx. So now we have to perform this integral. First, we can see that since there's square root of 2 over a here and here, we can just put it together and eliminate the square root. Okay, so how do we do this integral? The way to do it is to remember that there is a trigonometric identity that says that the product of the sines of alpha and beta is just going to be a half times cosine of alpha minus beta minus cosine of alpha plus beta. So now we can transform this into an integral that is going to be way easier to solve. So we just put this 2 over a outside, integral 0 to a of a half cosine of, okay, instead of alpha, let's just say that this right here is going to be alpha, this right here is going to be beta. So alpha is just going to be m pi over a x minus beta, which is n pi over a x, and this whole thing minus cosine of now the sum of these. So the sum is just going to be m pi over ax plus n pi over ax dx. Okay, so now let's just copy this. I'm going to put it up here. I know I forgot my A on the other page. Okay, so now we can simplify this. This half is going to cancel out this 2 right here. And we can factor what is inside of this cosine. So instead of that, we're going to have pi over ax m minus n. And this other cosine we can rewrite in a similar way, but we get whoop, I didn't mean to use my red color. Okay, so we are going to get that. Now, as I said, this integral is going to be much, oops, I meant to use this actually. Okay, wait a second, let me get rid of that. Whatever, doesn't matter. This integral is going to be way easier to solve. This is just a normal integral, so it's a very basic integral. So we're going to get 1 over a times sine of pi x over a, because the integral of cosine is sine, m minus n. And don't forget, because of the chain rule, we have to multiply here by the inverse, basically 1 over what would be the derivative of this, minus sine of pi x a m plus n times a over pi m plus n. Yes, and this whole thing has to be evaluated between 0 and a. So let's do that. We can cancel out this a with this here, and now let's evaluate. So this is going to be sine of pi a over a m minus n, and divided by pi m minus n. Now don't worry about this, because this case is only for those occasions where m and n are different, because remember, when m and n are the same, the integral that we started with, this right here, is just 1, because this is only for m different than n. When they are the same, we know that it is 1. Okay, so now this is when we evaluate the first at a, but when we evaluate it at 0, we get minus sine of 0 times this whole thing, but this is just 0, so there's no need to write this down. So now let's take a look at this right here. So we get minus sine of pi of a divided by a m plus n divided by pi m plus n. And there's also a minus the second term, so you get plus sine of 0 times whatever is multiplying, but that is also 0, so don't worry about it. Okay, now we can simplify these a divided by a's that are here, and we just get sine of pi times m minus n minus sine of pi m plus n. So the thing is, m plus n, m and n are both integers. So that means that both m plus n as well as m minus n are going to be integers as well. So what we are going to have in the argument here of the sine function is going to be maybe pi or 2 pi or 3 pi or 4 pi or whatever. It's always going to be an integer amount of pi. So that means that both of these are going to be separately 0. So this whole thing is going to be 0. Okay, so that is exactly what we wanted to prove. So it doesn't matter what m and n are, as long as they are different, then this is going to be 0. And when they are the same, it's going to be 1. So let us summarize this in the following way. So let us just write psi m of x, psi n of x dx. This is going to be 0 whenever m and n are different, or 1 whenever m and n are the same. This means, and this is what we mean when we say that these eigenstates, these wave functions, are not only orthogonal, but they are orthonormal from each other, because of this, basically. If they are different m and n, then their product is going to be 0, and when they are the same, their inner product is going to be 1, okay, because they are normalized. So, and in order to write this in a way that is a little bit less cumbersome, we are going to introduce what is called the Kronecker Delta, which we write as this Greek letter delta and m. So, and what this means is exactly this right here. So delta tells you if these two numbers are the same, then this whole thing is going to be 1. If they are different, it's going to be 0. So for example, if we get delta 1, 2, this is 0 because they are different. Delta 1, 1 is going to be 1. And also delta 2, 2 and delta 3, 3, for example, are going to be 1. But delta 2, 3 is going to be 0. Okay, so I hope you get the point. That is what this delta does. And this is the first part of these wave functions, very important. They are orthonormal to each other, and there's a property that will save you a lot of work in many situations. So that is the first part. Now we want to discuss the completeness, okay, completeness of these wave functions. So as we saw, if this psi of x is a solution to the Schrödinger equation, then since it's a differential equation, we can also introduce more solutions that are just linear combinations of these solutions. So we can get a more another solution just by taking linear combinations of our existing solutions. So what are those solutions? Let us write down our psi of n. This is going to be 2 over square root of a sine of 2 pi over ax. Now this, as some of you may recognize, is just the definition of a Fourier series. And remember, a Fourier series tells you that you can build any function with this series. That's basically the whole idea of the Fourier series. It can be proven through what some call the Dirichlet theorem. Dirichlet. That's more of a mathematical methods topic than in quantum mechanics. If there's a lot of you who would like to see the proof, you can tell me in the comments and maybe I'll do a video on it later. But at least for now, it's not really what we want to be covering. So I'm just going to assume that you understand that, and if not, that you just believe that for now. Okay, so what is the idea behind this? The idea behind this is that since we also have in the Schrödinger equation, we said we have this psi of x and t, and in order to solve it, we just assumed that we want to look for solutions of this separable form. But it's not always going to be the same. And I said only a subset of all solutions will be of this form. But what I told you is that it's not going to be a problem because these solutions will help us find all other solutions. And that is precisely because these solutions are a Fourier series that can generate any other function when you take enough of these n's, right? So what we want to do now is learn how to apply this concept of completeness to actually find this psi x comma t. So let us now do precisely that. Let's say that we take a linear combination of this to find our psi. So it just goes n from 1 to infinity, Cn psi of x. I'm just writing psi of x because it's shorter than to write this whole thing, times this e to the minus I e t over h. This has an n and n. Okay, so these are our solutions, but the problem is, I mean, we know what this is, we know what the energy is, but we don't know what these coefficients are. So we need to find a way to determine what these coefficients are. So the way to do that is to do something that is called the Fourier trick. A Fourier's trick. And what this does is that since we want to eliminate this this integral, is that I don't want to go ahead of myself. So first, let us take a look at this psi x comma 0, so that we can get rid of these exponential terms. So this is just going to be sum n equals 1 to infinity Cn psi n of x, right? This exponential is now just 1 because the exponent is 0. So now we apply Fourier's trick. What it says is that you have to multiply from the left by psi m of x, and then you integrate. And let's take a look at that. Now you might be wondering, and why that? And maybe you wouldn't have thought of that. That's fine. I mean, that's why it's a trick. I mean, if you hadn't thought of this, it's fine. I wouldn't have either. I don't think many people would have. That's why Fourier gets the credit for it. But the whole point of this is to exploit the orthonormality of these functions. So on the left, we just get, you know, this extra term, but on the right is where the real interesting things happen, because now we get this integral of psi m of x times, well, what we already had, the sum Cn psi n x dx. But now let's take a look at this, because this sum right here and this Cn depend on n, not on x. And this psi right here depends on m, not on n. So what we can do now is we can reverse the order of these quantities there. So we're going to get now the sum outside, n equals 1 to infinity of Cn, and now comes the integral mx. And what is the point of this? This is exactly why we do the Fourier trick, because now this right here is going to be the Kronecker delta, right? This is what we already saw. This is just an inner product between psi m and psi n. And we know that if the m and n are the same, it's going to be 1. If they are different, it's going to be 0. So instead of this integral, we can now write just the Kronecker delta. And now that we have the Kronecker delta, remember what this tells us. This tells us if n and m are not equal, then everything is 0. So in this sum, n will have many values, but only the value where n is equal to m will survive. So this sum is going to be only Cm. And this is our important, very important result. I'm going to write it here so I can highlight it. This is Cm. Now, if we are given the initial state, because that is what this psi of x comma 0 is. This is the initial state of our function. If we are given this initial state of our function, then performing this integral, because this psi m right here is just the normal solution that we found for this infinite square well, the square root of 2 over a sine of n pi over ax. So we can just perform this integral and we get our coefficients, and then we plug these coefficients into this equation right here and we get our wave function. And with that wave function we can compute whatever measurements we want to do. So we can find expectation values or whatever it is that we want to determine. So that is what we want to see with completeness. That is this whole point of completeness. Using that, we can find what happens to this. We can find the information about the system if we are only given what the system looks like at the beginning, which is very, very interesting and also very good, because in physics you want to be able to predict things, because so that you can measure them later. So this is and something that is very, very important, I almost forgot to tell you, is that these coefficients, remember, they have to add up to 1, right? Whenever you take these coefficients, they have to be 1, right? That's very, very important, because we're still talking about the the probability. I mean, this wave function may be divided into many solutions, many parts, but in the end, it has to be just equal to 1. It has to be still normalized. Well, so that is it for today. In the next few videos, we are going to be doing a few examples so that we can use all of these things that we have seen, calculate some expectation values, use orthogonality, completeness, and a lot of different things. So if there's any questions, just let me know in the comments. If you like this video, make sure to like it, comment, and hopefully share it with someone else who might also like it, so that you can support me a little bit and I can continue to do this. So I'll see you in the next video.